Hi. So in this exercise, we're concerned with the expected X-ray peaks that you will get for polycrystalline sodium. And sodium is a BCC, body-centered cubic, and it has a lattice parameter, as you can see here, and also we're radiating with a wavelength, which you can see here. And we are concerned with at what angles, so that you expect to see the first 5 diffraction peaks. In order to solve this, we need to look at what conditions need to be satisfied in order to get diffraction. So there are 2 conditions. The first condition is that the structure factor, which is proportional to the measured amplitude of the outcoming beam, has to be non-zero. And also that the change in wave vector has to be equal to a reciprocal lattice vector of the crystal. And since we're looking at the polycrystalline sample, this lattice vector here doesn't need to be in the direction of the reflective plane, since all different combination of planes are present in this at the surface if it's polycrystalline. And to calculate this, you sum over the form factor, which are local properties at all atom sites. So you sum over the form factor at the atom sites and multiply it with the phase factor. And this phase factor has to be equal to this, where you replace the change in wave vector with the reciprocal lattice vector, since that's one of the conditions that we need. And when you do this, you can calculate this dot product, and you get this expression here, where x and y and c are the x, y, and z coordinates for the 2 atoms. You sum over the 2 atom positions, right? You sum here, meaning that you sum over j, and j equals 1 corresponds to the 0, 0, 0, where there is an atom at the 0, 0, 0 position. And then you also have an atom at, since it's a BCC, right? So you have an atom in half, in the middle of the cube. And so if you do that and calculate the sum, you get a structure factor which is proportional to this. Right? So if you look at this expression here, you can see that when h plus k plus l is even, this expression here becomes 0, meaning that this is non-zero, the whole thing is non-zero. So we require that h plus k plus l is even, right? And in order to calculate what angles we're supposed to see, right, we use the fact that, that the change in, like this. So now you can see here. So you have this change in wave vector, which just has to be equal to a reciprocal lattice vector. And you use that together with the conservation of momentum. And this gives us, this is a good exercise to do at home. It gives us, you can calculate the expected angles for a given plane with the Miller indexes h, k, and l. So, and also the lowest allowed diffraction angles can be calculated, and if you do the calculations, you get these angles for the different planes. And if this would have been a simple crystal, not a polycrystalline structure, then you would only get planes here corresponding to the actual plane that you're illuminating. That you have the planes that your X-rays are diffractive of. Hi. So in this exercise, we're concerned about finding the cubic metal structure from an X-ray diffractogram. And To our help, we know that the radiation we're using has the wavelength that you can see here, and we also know that the crystal we're looking at is a polycrystalline cubic metal. And in a diffractogram, what basically you get is a set of peaks at certain angles, and we're going to use this and try to find partly the structure of the crystal, but also the lattice parameter A. So in order to do that, we need to calculate what the structure factor is for different types of crystal structures. So if we have a simple cubic structure, we only get the form factor, right, for the atom. And if we have a BCC, we will get two factors. One which is basically where the atom is in the corner of the cubic cell, and then we want one contribution from where the atom is in the center. And for FCC, you will get a structure factor which is basically one for an atom at the corner, and then we will get contribution from atoms on each of the three faces. Basically, that's it. And what we can see is that for the first form factor, all peaks will appear in the structure. And so the question is, is this all peaks for that are possible, or is this only peaks that where the sum of HK and L are even, or is this the peaks that corresponds to that HK and L are all even, or they're all odd, which will give you basically a non-zero structure factor for the FCC. And in order to check that, we'll actually use these angles, right? Theta is the angles here, and then we will calculate what the first planes will be with the lowest angle. So if you do calculate this for the particular crystal, it should always be constant, right? Since this is equal to the wavelength we're using to radiate, and then divided by the lattice parameter, and this stays constant. So in this table here, we should use this expression, and if we get a constant value, we know that we have the right crystal structure. So basically what we do is that trying to match the angles with the expected planes we get for a certain lattice and for a given peak number. And then we print out the values for lambda squared divided by 4a squared. And it turns out, you can do the calculations yourself, is that only for the FCC case, these values, as you can see here in my diagram, is that for the FCC lattice, this is the only case where this A here, representing this value here, is constant. So you can do the BCC and the simple cubic lattice yourself if you want, and check that for the first valid numbers. Here you can see that these peaks are only where HK and L are all even or all odd. In the BCC case, it would be possible to have other planes that could scatter the light, meaning that you get different numbers corresponding to other planes, which will yield a non-constant value for these. And basically we use this relation here, that A is equal to this value, and then we calculate the lattice parameter by just solving what A is in terms of the big A, and we get the solution that the lattice parameter is 5.51 angstroms. Hi. So in this problem, we're going to look at crystalline silver, and we're going to look at what are the expected diffraction angles for crystalline silver. And we know the lattice parameter, and we know that the silver has the crystal structure FCC, but we don't know in which direction the sample is cleaved. That is, what surface do we have that the light is reflected out of? Well, we know that it's either 1, 0, 0 plane, the 1, 1, 0 plane, or the 1, 1, 1 plane. And we also know the wavelength, obviously, and also we would like to then calculate the two first diffraction angles for these three cases. And in order to do that, we first calculate the structure factor for FCC, or basically we'll put down the diffraction conditions first. That the structure factor is non-zero, and that the change in wave vector is equal to a reciprocal lattice vector of the crystal. And we can do that by summing over the form factors for individual atoms in the cell and multiplying that with this phase factor here. And by inserting the position of the atoms in an FCC cell, well, basically all these are in units of A, which is the lattice parameter. And if you put them in, you will get an expression that will be zero, or will be non-zero for the cases where H, K, and L are all even, or if they're all odd. You can put out the expression and you will see that that's the case. And in order to calculate what the expected angles are, we basically use this relation here and derive the Bragg's law, and then we calculate what theta is in terms of H, K, and L, and what lambda and the lattice parameter. So basically we can then say that the allowed planes for diffraction from the different cleavings is basically for the 1, 0, 0 plane, it has to be either 2 or 4, because 1, 0, 0 or 3, 0, 0 doesn't have all H, K, and L even, or they're not all odd. So this is only plane because they need to be parallel to the surface, right? And for the 1, 1, 1, 0 plane, which these are all proportional. If you have the same value here and here, they will all be perpendicular or parallel to the plane, the surface plane. And these are basically the allowed planes that you can have. And for the 1, 1, 1 case, you actually get you have odd numbers here because it's allowed to have all of H, K, and L odd. And basically we use this relation here, put in these values for H, K, and L, and then calculate what the two first diffraction angles are for the three cases. And the result is basically this. So for the 1, 0, 0 case, this is what the angles you expect to get diffraction at, and for the 1, 1, 0, these are the angles, and so forth. So this was this problem. Hi, so in this exercise we're concerned with the structure factor for strontium titanate. And in strontium titanate, the titanium atoms are located in the corners of the cubic cell, and the oxygens are located, as you can see here in the figure, on the sides. And the strontium atom is in the middle. So basically, what is the structure factor? And in order to calculate the structure factor, we need to look at what the structure factor is defined as. And basically, the structure factor is something that is proportional to the amplitude per unit cell. So to calculate the structure factor, basically, so here is the amplitude, the scattered amplitude, or a factor that is proportional to that. And basically that is proportional to the integral over the electronic density times the phase factor. And you can basically replace this with the reciprocal vector since due to the diffraction conditions. So basically this is the change in wave vector basically, but then you replace that with the reciprocal lattice vector, and that's what you get. So so this part here is the structure factor. But then what you can do is that you can replace the electronic density by the electronic density parts contributing from each atom. And then you sum over all the atoms, and what you do is if you replace then the electronic density with this expression, put that in, you get a sum over these atomic site electronic density contributions. And then what you can do is you can factor out this part together with that one and call it the form factor. And when you do that, you get this expression for the structure factor. And now basically we look at what the atomic sites are for the different atoms in strontium titanate. And basically we have the titanate, the titanium position is in the corner, so that's 0, 0, 0 in units of A. And then we have the oxygen atoms, which are located on half pass. There are 3. There are basically in the unit cell you could see in total 12, but they are shared by 4 different cells, meaning that there are a total 3 atoms, and they are located accordingly like this. And the strontium is in the middle, which is basically in units of A, half in all directions. And putting this together, we basically get the structure factor, which is putting in the relation that we had before. This gives basically the phase factor vanishes, so you get 0, or you get 1 for the structure factor there. Sorry, for the phase factor. And for this case, you get one of these exponentials as the phase factor for each of these atoms, and then the last atom is basically just when you put in reciprocal lattice vector equal to so you put in an atomic site equal to this, and when you multiply with a reciprocal lattice vector corresponding to HKL, this is what you get. So this is the whole expression for what the structure factor for strontium titanate looked like.